When answering essay questions about trends, one, never just state the trend, such as the element is more to the right or further down. That's not going to get you any points. Two, be specific. Don't use pronouns such as it or the element. Be very specific about which one. Also refer to both of the atoms or ions in the question. Don't just say that hydrogen is smaller and leave it at that. Smaller than what? Why is it smaller? When atoms are in the same energy level, as in when you're going from left to right or right to left, those are in the same energy level, you should be referring to effective nuclear charge, which is basically how many protons you have. As you go to the right, you have more protons in the same number of energy levels, so you have a greater effective nuclear charge. When you're comparing atoms that are in different energy levels, in other words, up and down, you should be referring to the distance from the nucleus, energy levels, and electron-electron repulsions. As you go down, you have more energy levels. The electrons are going to be farther from the nucleus, and there would be more electron-electron repulsions because you have more electrons. Coulomb's law shows that the force of attraction between two oppositely charged particles is directly proportional to the magnitude of the charges and inversely proportional to the distance between those charges. You don't have to plug anything into this equation, but Q1 and Q2 refer to the charges. So when we're referring to the nucleus and the electrons, like how much energy it takes to remove an electron, your charge of the nucleus would be Q1, that would be your effective nuclear charge, and the electron has an opposite charge. And then distance, how far away from the nucleus are those electrons? So it would be the distance between the electron and the nucleus. So the charges come into play and the distance. So one trend that you're going to have to be able to explain is ionization energy. Ionization energy is the energy required to remove an electron from an atom or an ion. First ionization energy is the energy to remove one electron. That's generally what we're looking at when we're comparing atoms and their ionization energy. So when sodium, it would gain energy to turn into sodium ion and an electron. Sodium's not going to just lose an electron, it's going to have to absorb energy. How much energy is its ionization energy? If sodium ion was to lose a second electron, this energy would be the second ionization energy. The second ionization energy is always much higher than the first ionization energy. Why do you think that would be the case? Pause the video and think about that, and then restart when you think you have an idea. If you said because when the first electron is removed, the atom is neutral. But when the second electron was removed, the atom was an ion which had a positive charge. That positive charge is going to have a greater pull on the electrons because the second electron is closer to the nucleus. It's actually a core electron. So it's always going to require more energy to remove the second electron because of that positive charge. I have more protons to electrons. So the trend for ionization energy is it increases as you go up and to the right, as you can see from the picture. So draw your arrows for the general trend. Remember, this is a general trend, not a reason why. you need to be able to explain why it increases as you go up and to the right, which is our next two slides. So ionization energy, or the energy to remove an electron, increases as you go to the right because there are more protons attracting the same number of energy levels of electrons. So there's a greater effective nuclear charge requiring more energy to remove an electron. So we can see that in the picture. Here we have sodium and chlorine. They both have 3 energy levels, but sodium has 11 protons attracting its electron in the outer ring, or valence electron, while chlorine has 17 protons attracting its valence electrons. Since chlorine has a greater effective nuclear charge, it's going to require more energy to remove this electron from chlorine than this electron from sodium. As you go down a group, ionization energy decreases because there are more energy levels of electrons, and thus more electron-electron repulsions, and the electron is going to have a greater distance from the nucleus. So it has less attraction to the nucleus. So it requires less energy to remove it. You can see that in the diagram over here. Our 2 electrons, this one, there's only 2 energy levels. Therefore, the electron is much closer to the nucleus. There's less electrons between the green dot and the nucleus, so there's less repulsions. The one over here has 4 energy levels, so there's lots of electrons which are going to be repelling this green electron. And there's a greater distance from the nucleus, which means that there's less attraction with that electron and the nucleus. The first ionization energy of magnesium is 738 kilojoules per mole, while sulfur is 1005 kilojoules. So magnesium is located here and sulfur here. So come up with your explanation on why magnesium is less than sulfur. Restart when you've come up with your answer. Remember, make sure that you have a full, complete answer in complete sentences. So remember that we need to be comparing them. So we need to talk about both atoms. So magnesium and sulfur both have 3 energy levels. But magnesium only has 12 protons versus sulfur 16 protons. Since sulfur has a greater effective nuclear charge, sulfur requires more energy to remove an electron. So I'm saying that they have the same energy levels, and that's why it's important for me to mention the protons, because it has to do with the effective nuclear charge, because they have basically the same energy levels, which is going to be roughly the same electron-electron repulsions and the same distance from the nucleus. So on this one, we're comparing potassium and cesium, which are both in group 1A. So there's potassium and there's cesium. Go ahead and pause the video after writing your response for this one. So you should have cesium has 6 energy levels of electrons, while potassium only has 4. Since cesium has more energy levels and more electron-electron repulsions, cesium will require less energy to remove an electron, as cesium's valence electrons are further from the nucleus. So I compare what's the same and then what makes them different. Since it's in the same group, you should be referencing energy levels, electron repulsions, and distance from the nucleus. On this one, it says phosphorus's ionization energy is 1060 kilojoules per mole, and sulfur is 1005 kilojoules per mole. What accounts for this decrease? So first off, we would expect sulfur to have a higher ionization energy than phosphorus. It's further to the right. That's what would follow the trend. So on the AP test, never say Well, this information must be wrong because sulfur should be greater than phosphorus. They're telling you what the data is. You have to come up with some rationale or some reason that this discrepancy occurs. So I'll give you a second to come up with why you think it occurs. I'll give you a hint to draw the orbital diagrams showing the electrons in the different orbitals. Restart when you think you have a reason. So phosphorus and sulfur both have their electrons in the 3p. Phosphorus has 3 electrons in the 3p, while sulfur has 4 electrons in the 3p. So we're saying this electron requires less energy to remove than this electron. Recall that electrons are negative and they don't pair up until they have to because there's going to be repulsion when they pair up. That's what causes the decrease in ionization energy for sulfur. There is more electron repulsions between the paired electrons in sulfur, which causes the electron in sulfur to be removed more easily. Here's another type of question that you could see where it says, which atom has the largest first ionization energy? Well, first ionization energy means the energy to remove the first electron. You don't have to, but it may be helpful if we say which element each of these are. So this is neon, this is sodium, and this is magnesium. Since it's a multiple choice question, I could just say, well, the trend is up and to the right. So of these, neon is furthest up and to the right, so I would expect it to have the largest first ionization energy, which is correct. But if this wasn't a multiple choice question and it was a free response, and it said why, or which one would you expect to have the largest first ionization energy and why, you would have to come up with an explanation, and saying because it's further up and to the right isn't going to cut it as your explanation. So if we look at it, if A loses an electron, it's going to lose it from the 2p. In B, if it loses an electron, it's going to lose it from the 3s, and C would lose it from the 3s as well. Well, the 2s is closer to the nucleus, therefore it's going to require more energy to remove it. So A would lose a 2p electron, which is closer to the nucleus, and thus a greater attraction with the nucleus. This question says which has the smallest second ionization energy. That means the easiest to remove 2 electrons. Well, on A, if I lose 2 electrons, they're both going to come from the 2p. On B, I'm going to lose 1 from the 3s, and then I'm going to lose it from the 2p. While C, I can lose 2 in the 3s. So, on C, since I'm losing them both from the 3rd energy level and I haven't gone into the core electrons or the 2nd energy level, it must be the easiest to remove 1 from C. So if C lost 2 electrons, it still would not have lost any core electrons, which are the 2p. Electrons which are closer to the nucleus, and thus attracted more. A and B would have to lose core electrons, or 2p electrons. This one isn't in your note packet, but pay attention. Another way that you can see ionization energy questions is given a table like this, and it says how many valence electrons does this element have? Or which element is it? So if it tells you that it's in period 3, you could figure out which element it was based on how many valence electrons it has. So to do that, these are my ionization energies. It says first ionization energy, second ionization energy. Notice that I have a giant jump there. The reason I have that giant jump is what we were seeing a second ago. There's sodium's electron configuration. When it loses the first electron, it loses the 3s. Well, that's a valence electron. It's farther from the nucleus, so it only requires 495 kilojoules per mole. While when I lose a second electron, I'm losing it from the 2p, which is much closer to the nucleus. And that's what causes that dramatic increase in ionization energy. For magnesium, notice it has 2 electrons that come off relatively easily. The second one always requires more than the first one because I am still taking it from a positive ion. But after 2, I'm taking core electrons, which are going to require a lot more energy. Aluminum, since it has 3 valence electrons, notice I have a huge jump in energy here. Silicon has 4 valence electrons. That's why I have a giant jump. Phosphorus has 5 valence electrons. Sulfur, 6 valence electrons. Notice for chlorine and argon, you don't see any big jump because chlorine, I don't have the 8th valence electron over here. That one would be where my big jump would be for it. So if I wasn't given this as sodium, but I was told that it was in period 3, I could say, well, I know that it has 1 valence electron. Which element has 1 valence electron in period 3? Or maybe it says, given this element's ionization energy data, what formula would it make with chlorine? Well, this element X has 3 valence electrons, which would mean it would make a +3 charge generally. Chlorine's a -1. So that would be the general formula of that compound. We get ionization energy data from PES, or photoelectron spectroscopy data. So a sample is irradiated with a beam of UV or X-rays, or a combination of the two, causing electrons in the sample to be ejected. Remember that we said that core electrons are going to be removed with X-rays because X-rays are a lot higher of an energy source than UV, so they're able to penetrate the atom better, while valence electrons are removed with UV. To read the PES graph, you're going to look at the x-axis and see where the highest energy is. It could be on the far left, it could be on the right, it could be, if it was in multiple layers, it could be on the top, it could be on the bottom. Find on the x-axis where the greatest amount of energy is and say that that's your 1s orbital. So the 1s must be closest to the nucleus. Therefore, it would require the most energy to remove it. Then, either on a separate line, or sometimes they'll put these little gaps in there. So we have a giant gap in energy. Then we have another peak. This peak must be the 2s2. Notice that they're the same height because the height, or the intensity, refers to the number of electrons. So after the 2s, we usually come to 2p. Notice that my 2p is about 3 times as high as my 2s because there's 2p6. There's 3 times the number of electrons in that orbital. So next, after 2p, I would get 3s. It's the same height, so that must mean that there's 2 electrons in there. So 3s2 corresponds to magnesium. So this is magnesium's PES graph. You could explain it by showing the electron configuration above it, saying that there's 4 peaks, which correspond to 4 sublevels. And the last peak is the same height as the first 2, which means that there must be 2 electrons in that 3s orbital or sublevel. On this one, It says that the 1s electrons have been emitted. So you're going to start with 2s. Go ahead and pause the video and figure out which element this is by labeling your electron configurations like we did previously. So you should have started over here. So this was 2s2, then 2p6, 3s2, 3p6. Our next peak should be 4s2, but that wouldn't make sense that that's 4s2 because it's taller than this 3p. So after 3p6, we have 4s2. This must be 3d10. All of your third energy level are equal distance from the nucleus, or relatively the same distance from the nucleus. Therefore, they're going to require about the same amount of energy to remove them. After the 4s, then we have 4p. We compare it to this one, and they're the same height. So that must be 4s or 4p6. So if you said krypton, you are correct. So first off, which element does this PES graph belong to? Go ahead and pause the video and figure out which element. Restart when you have it. So you should have done 1s2, 2s2, 2p6, 3s2, 3p. But this time it's not 3p6. It's higher than 3p2. It's about the same, or it's about half the height of 2p. So this is 3p3. So if you said phosphorus, you are correct. The follow-up question says circle the peak in the graph that contains the first electron that would be removed from the atom. This would be referred to as the first ionization energy. And then state its ionization energy. So if I was to remove an electron, I wouldn't remove it from the 1s. That one would require the most energy to remove. If I was to remove an electron, I would remove it from the 3p. It's the farthest from the nucleus, and it would require the least amount of energy. How much energy to be exact? 1.01 megajoules per mole. That would be phosphorus's first ionization energy. I could then convert that ionization energy to wavelength or frequency or anything else I needed to. All right, finally, based on the spectrum for helium here, which model, 1, 2, or 3, best represents the electron arrangement for helium? Justify your choice and state whether the graph does not support and why the graph does not support the other two incorrect models. Go ahead and pause the video and figure out which model supports it. So you should have said model 3, because according to the PES data, there should be 2 electrons, not 1, like in model 1. Model 1 only shows 1 electron. And there should only be 1 electron shell based on there only being 1 peak. Each peak represents a different sublevel. We only have 1 peak, so we can't have electrons in 2 different electron shells.